Imagine a world where energy is limitless, where the power of the sun is harnessed not from the distant filtered rays that reach Earth, but from the scorching, unfiltered fury of our star's closest neighbor, Mercury. The smallest and innermost planet in our solar system, orbits just 36 million miles from the sun, a blistering wasteland where temperatures soared 800 degrees Fahrenheit or 430 degrees Celsius during the day, and plunged to negative 290 degrees Fahrenheit, minus 180 degrees Celsius at night. Yet, despite its extreme conditions, Mercury holds an untapped potential that could revolutionize humanity's energy future, solar power on an unimaginable scale. But what if we dared to build solar panels on Mercury? Could we overcome the planet's deadly environment to create the most efficient power station in the solar system? And what would such an endeavor mean for Earth, for space exploration, and for the future of civilization itself? A silent, scorched world orbits perilously close to the sun, a place where daylight is a deadly inferno, where the very ground beneath your feet could melt lead, and where the night is a frozen abyss colder than Pluto. This is Mercury, the solar system's forgotten sentinel, a planet so extreme that its very existence defies human intuition. Yet within its hellish landscape lies an opportunity so vast, so revolutionary, that it could redefine civilization itself. What if we covered Mercury in solar panels? The idea is as audacious as it is terrifying. Mercury receives 6 to 10 times more solar energy per square meter than Earth. A single solar array there could theoretically power entire continents back home. But the obstacles are staggering. 800 degrees Fahrenheit heat, solar storms that fry electronics, and a year-long night that plunges the planet into negative 290 degrees Fahrenheit, minus 180 degrees Celsius darkness. This is not just an engineering challenge. It is a test of human ambition, survival, and our place in the cosmos. If we succeed, we unlock near-limitless energy. If we fail, we risk unleashing forces we cannot control. On Earth, solar panels operate at 20 to 25% efficiency at best, hindered by atmosphere, clouds, and nighttime. But Mercury, no such limitations exist. With no atmosphere to scatter sunlight, solar irradiance is direct, brutal, and unrelenting. A single square kilometer of solar panels on Mercury could generate 10 to 15 gigawatts, enough to power millions of homes indefinitely. But how do we get this power back to Earth? Traditional cables are impossible across millions of miles of space. The solution? Microwave or laser power beaming, a technology already in experimental stages. Giant orbital transmitters could convert electricity into focused microwave beams shot toward Earth, where giant rectennas, or rectifying antennas, capture and convert them back into usable power. The risks? A misaligned beam could accidentally scorch cities or disrupt satellites. The precision required is beyond anything humanity has ever attempted. Beyond Earth, Mercury could serve as the ultimate refueling hub for interstellar missions. Solar-powered ion drives or fusion reactors could recharge here before venturing to Jupiter, Saturn, or beyond. Mercury's low gravity, just 38% of Earth's, means launches require far less fuel, making it the perfect interplanetary pit stop. This is not just a thought experiment. It is a deep dive into the possibilities, the dangers, and the staggering implications of turning Mercury into a cosmic power plant. The sun's overwhelming power. On Earth, solar panels operate under filtered sunlight, with atmospheric interference, clouds, and nighttime reducing efficiency. But Mercury has no atmosphere, no air, no weather, no obstructions. Solar radiation here is 6 to 10 times stronger than on Earth. A single square meter of solar panel on Mercury could generate up to 10 kilowatts, enough to power multiple homes back on our planet. But how would we get this energy back to Earth? Traditional cables are impossible across millions of miles of space. The solution? Microwave or laser power beaming, a technology already in experimental stages. Giant orbital transmitters could convert electricity into focused energy beams shot toward Earth, where giant rectennas, or rectifying antennas, capture and convert them back into usable power. The risks? A misaligned beam could accidentally scorch cities or disrupt satellites. The precision required is beyond anything humanity has ever attempted. Beyond Earth, Mercury could serve as the ultimate refueling hub for interstellar missions. Solar-powered ion drives or fusion reactors could recharge here before venturing to Jupiter, Saturn, or beyond. Mercury's low gravity, just 38%,
makes it an irresistible long-term goal. Harnessing Mercury's power could propel humanity into a Type 1 civilization on the Kardashev scale, capable of utilizing all energy available on its home planet. But at what cost? Environmental destruction of another world? The risk of creating an unstoppable energy monopoly? Or worse, unleashing forces we can't control? Mercury is not just a planet. It is a test of ambition, ingenuity, and responsibility. To conquer its fires and harness its light would mark one of the greatest achievements in human history. But with such power comes peril. Will we rise to the challenge, or will the dangers prove too great? The answer lies